Our next topic is shape control by curves. And the work we introduce here is called fiber mesh. And what we propose is an extension of the previous technique, which called sketch-based 3D modeling. And the difference is that original sketch stays and works as a handle. So here, the input is very similar. You draw something and you get 3D shape. However, unlike previous system, this curve stays on the surface, and then you can grab them and move around, and then they form the shape. Let me show you a demo. So again, input is very similar. User just draw a line, and the system inflates it. However, as you see, your input stroke stays there, and then serves as a handle. So you can grab them and move upwards, and then surface continuously changes. And you can see it from the top, and then you can pull it sideways to change the shape. So in this way, you can get more control, and you get more smooth shapes, which was not possible in the polygon-based system. And you can also add more control curves like this way, and then you can grab this thing to change the shape. And then, like previous system, you can also add an arm. And from sideways, you can pull it down to change the shape. And here, as you see, we have two kinds of curves. So blue curves is a kind of smooth constraint, and red curve is, as you see, a sharp constraint. And of course, you can change the categories. For example, if you change them to blue, as you see, you will get a smooth transition. And if you want, you can also erase them to remove any constraint. And you will get a very smooth shape. Another example is here. So you draw a shape here, and then you draw a shape here. And here, this is a little bit too low tuned. Then if you want, you can make them sharp. And then you can get this kind of shape. Let me show you a couple more examples. So here, you get this shape. And then you can cut it here like this way. And you get the sharp shapes. And then if you erase these parts, you can get shape. So here, smooth, sharp discontinuity here, but smooth patches going around, and then again it meets as a sharp crease. This kind of thing is not easy to do with other approaches. You can use implicit surfaces, but implicit surfaces are always smooth. And if you use this discontinuous patches, then patch boundary is always sharp or smooth. And this is not easy. And after combining these operations, you can get reasonable shapes like this. You can make this kind of masks, or human body, or arms and so on. And the point here is that traditional methods requires a user to design these models by manipulating individual control vertices. But here, what user control is always the curves. And then we hope that this is more intuitive and more efficient. And let me describe the algorithm behind the scenes. So basic idea behind it is that user controls the curves, and the curves defines the boundary, and the system automatically generates a smooth surface based on the curves by running a continuous optimization, trying to make a smooth surface defined by the curves. So that's the basic idea. And let me describe the details. So curve deformation takes handle position as input, and then generates curve geometry, updated curve geometry. And the surface optimization takes curve geometry as input, and then generates smooth surface. And let me describe the curve deformation first. So curve deformation works like this way. So you have this shape, input shape, and then each segment has three-dimensional coordinate frames. And then if you pull one point upwards, and then a system will deform the entire curve. And then as you pull upwards, all coordinate frames also rotate together. So what we do is simultaneously updates edge position, edge length, and also rotation coordinate frame or individual segment, curve segments. And this is a quick overview. Please refer to the paper to the details. But briefly, what we do is minimize this functional by moving around vertex positions and edge rotations. So we try to find very good, more smooth vertex position and edge rotation that minimize this. And what we minimize is here is a difference. So this is a small Laplacian, which means the difference of the current position from the surrounding position. And then the current difference is rotated and it is compared to the current updated Laplacian. And this preserves the local details. And this one tries to minimize the difference between neighboring rotations. So this tries to achieve smooth rotations. And then this one tries to minimize difference between current position and the position of this one is position and nearby positions, so which means smooth positions. So this tries to minimize the difference between original position and updated position. Similarly, this one tries to minimize previous current rotation and updated rotation. So by solving this system tries to find a smooth deformation. And next one is surface optimization. And surface optimization takes as input a curve geometry and mesh topology. This is the input. And then system automatically generates smooth surface. To do so, system basically tries to minimize variation of curvature. Curvature is how curved the surface is. And then by minimizing the variation curvature, system tries to generate smooth surface. And in a mathematical representation looks like this. So Kn is a curvature, and then Kn derivative in both principal curvature axis and secondary axis. And then this represents the curvature, and then a curvature variations, and then we try to minimize this. And unfortunately, this is non-linear problem, and it's not easy or efficient to compute. So we approximate this by a couple of stepwise linear computations like this. A little bit complicated, but roughly we have two passes. So one is so left flow computes curvatures. So we first compute curvatures, which is a scalar values, and then by blending or smoothing out, then we get target curvatures. So as you see, originally curvature has many variations, but by smoothing out, you get more uniform target curvature values. So we tried to obtain these curvature values. And from these curvature values multiplied by a surface normal, you get target Laplacian vertices, vectors. So we try to obtain these Laplacian vectors. In parallel, we also compute edge lengths. So we first compute current edge lengths, and then we compute target edge lengths by blending or smoothing out. And then multiply this target edge length with current edge vectors, you get target edge vectors. And by combining these target Laplacian vectors and target edge vectors, we solve a least squares problem, and you get updated geometry. And we repeat multiple times, and then you get optimized smooth shape. So original paper was called Fiber Mesh, designing freeform surfaces with 3D curves. And a similar technique that is trying to gradually changing the shape considering local details was originally presented as sketch-based interface for detail preserving mesh editing. And also our technique is kind of running surface fairing continuously. And it was inspired by work by a geometric fairing of irregular meshes for freeform surface design. And we recommend to take a look at these works. Thank you.